You have stuff for me.
I'm walking. You're like reminiscing. I'm gonna be a good student. I'm gonna be a good student. Trust. I'm a good student. I try. Thank you.
A long time ago, August, I said that calculus was developed to solve two problems. The first of which was tangent lines, finding a line tangent to a given curve. The second one is the quadrature problem. The what? Algebra, and as a result calculus, are fairly recent developments mathematically. Algebra itself was only really developed into the thing we see now in the 1400s and 1500s. Before that, math is all done in words. You take the cube of the number here and add it to you write it out in sentences. As a matter of fact, in order to help you remember these things, we turned them into sing-song poetry. Schoolhouse Rock, anybody? It works really well, you can remember. ABCs are sung that way so people remember them. I hate doing mathematics this way. Algebra was developed to symbolically manipulate things that we were manipulating geometrically. And in Greek mathematics, if I wanted to say, what is the area of a shape, I had to physically make a square with the same area. A quadrature. This sounds stupid. Here's a rectangle. What's its area? You just have to count the boxes, right? If I'm a Greek mathematician, imagine there's no grid boxes here. A Greek mathematician would say the only way I know the size of this is to build a square whose area matches this. Bigger problem. The only tools permitted in Greek geometry are a compass and a straight edge. The thing you draw circles with, and an unmarked ruler. So I can take this length and I can draw a circle where that's the radius. And I can start doing things. By the way, for me to get from a rectangle to a square whose area is the same size is 4 pages of geometry. By the way, if I actually look in my geometry book, you know what the geometry book will show me? It'll show me that picture. And then it'll say, you do this and this and this and this, and that's the picture you get. And you'll pardon my bluntness, what the is that? The square here has the same area as that rectangle. But that is by no means a simple process. I like the idea of just going, it's 3 by 5, so its area is 15. But I would need, as a Greek geometer, to say, that means I can make a square whose length is the square root of 15 by the square root of 15. In case you're interested, all mathematics till the development of algebra is done this way. Algebra comes into existence in the early 700s. The symbols for algebra don't get invented till the 1500s. I hate that. But a quadrature is find me an area. I have some graph of some function. I want the area in there. I clearly can't use a rectangle. That's got a curvy top. I can't use a triangle. I could use multiple. Maybe I could break this up into multiple shapes. Let's stick with easy shapes. Greek geometry was absolutely thrilled with the idea of triangles. So Archimedes came up with the idea of, I'm going to fill this in with triangles. And what you do is you pick a point on your curve and you take that spot and you connect it to the base. And now you've got a triangle, and you know the formula for the area of a triangle. And then you do it again. And you connect it, well, instead of connecting it to the base, you can connect it to these lines, right? And you see how you have extra area left in here? Oh, that won't work. I got to go in because I can't cross out of the region. And I'm going to keep filling in these bits with straight lines in lots of different places. And eventually, I will exhaust all of the area. And I'll be able to add up all the triangles. And that's called Archimedes' method of exhaustion. And I'm not sure if it's called the method of exhaustion because it eventually exhausts all the areas, or if it exhausts me doing it. Because that sucks. Let me make a practical example. Let's pick a particular function. You should be able to create a graph and draw the picture of this area fairly easily. What's this graph look like? It's a parabola. It's got its vertex at 0, 0. It goes through the point 1, 1. Like that. It's not a straight side. I can't use a triangle. I could break this up like I did with the triangles up above, but as we already determined, that's not nice. Bunch of different people start looking at this. A guy by the name of Riemann comes along and he says, I know what I'm going to do. I'm going to imagine cutting this into strips vertically. And then I'll pick in each strip a height. For the moment, I'm going to make my life easy, and I'm going to divide the piece from 0 to 1 along the x into even sections. They don't have to be, but for the moment, I'm going to use even sections. How about 4 sections? That number is arbitrary. I just pulled 4 out of thin air for the moment. Now I'm going to draw a vertical line until I hit the curve at each of those x values. And those are my 4 strips. And then I can use a rectangle if I put a height on each strip. But we get to choose where in each strip we put the height. So here is strip number 1, and strip number 2, and strip number 3, and strip number 4. So strip 1, strip 2, strip 3, strip 4. Riemann said, this graph is increasing on this interval. If I were to use the rightmost edge, the height would be lower than the actual area of that strip. I'm going to call this R4, a right choice with 4 strips. And R4 is going to be the area I get. So I think to myself, I need a width and a height to make a rectangle that I know will fit under each of those strips. So if I use the right edge for a height, this first piece has a height of what's the right edge? Said that twice now. I screwed up. Stop. Right edge. Right edge is here. Yes? We're not going to be under. We're going to be over. That's okay. We'll be over. Lefts will be under. We'll do those next. What happens with what's the height of that? I do know because I know the x values. We divided it into 4 parts evenly, right? So that means this one is half, this one is a quarter, and this one is 3/4. And this is the graph y equals x squared. So I can find the height by putting in the x value. The height here is 1/4 squared. But that's just the height. The area of that box is height times width. So I multiply by the width. That's strip 1. I got to do it 3 more times. Second strip. Third strip. Fourth strip. Right? And for each of these, I can use these numbers to determine the height. Give me a number. You don't have to leave it as a fraction. You can give me a decimal. I'm okay with that. Well, because this strip, number 4, the right edge has x equal to 1, right? So I plug that in to get the height of strip number 4, height times width. In all of these, it's height because that's x squared times the width of the strip. And that rightmost edge on the last rectangle is a height of 1. Bunch of button pushing. Give me some calculations. Tell me what this area is. I am hoping you all got this same decimal. Now, I don't know what the actual area under my curve is, but I know whatever it is, it's less than this. So I have an upper bound. The area's got to be less than 0.46875. Let's switch from the right edge to the left edge. If I do a left sum, I'm going to get an area that's below because I'm missing stuff, right? So this will be a lower bound. Again, my width is still 1/4 for each strip. And the height will be a y value on the left edge of each strip. So in my first strip, the left edge is x equals 0. For my second strip, the left edge is now 1/4. My third strip, my left edge is now 1/2. And for my fourth strip, the left edge is now 3/4. Again, give me a number. And now I can say with complete certainty, my area should be bigger than this. Because you can see I missed a bunch of spots. In R4, I had excess. That's an overestimate. In L4, I'm deficient. I have an underestimate. Say what? I could average these together, right? I could take the left plus the right, divide by 2, and hope for the best. I could. Yes, but it's much uglier and it depends on our number of rectangles. Hold that thought, I promise I'll make one. What do you get if you add those together and average them? Say again? Which I would expect to be closer to the right answer. Yes? If one is under and one is over, the average should be closer than either of them. Right? Not bad, not bad. Riemann said, look at the picture. I missed quite a bit of area in this L4. In R4, I had a lot of excess area. Again, I am short, ellipsos. I am over, hyperbolos. Hyperbolic reactions. To speak hyperbolically, it's the same thing as hyperbola and ellipse. It's the same damn words. But it was to mean excess or deficiency. I could make this better. I could make my approximation closer if I split these even further. What if instead of doing 4 rectangles, I doubled that? And I did 8. I'm not even going to do the calculations. Let's just draw the picture. If I do L8, I'm going to use the left edge. If I do R8, I'm going to use the right edge. What do you notice about my deficiency and my excess? It's smaller. So L8, I'm sorry, and R8 should be closer to the right answer than L4 and R4. So I could say that L4 was smaller than L8 and R8 is smaller than R4. And the right answer should be somewhere in the middle still, yes? There's less excess, there's less missed. This makes sense. How can I make it better still? More sections. Page 375. Lots more sections. Here's L10. Here's R10. Here's L30. Here's R30. Here's L50. You can barely see the amount that we're missing. Here's R30. You can just barely tell that we're over the top. How can I do better? More. I'm still not satisfied. Let's keep going. As a matter of fact, let's let the number of slices go to infinity. We'll take a limit if that limit exists, then that limit should be my area. But that limit has to exist, and it has to be the same for both the right side version and the left side version. If these are not the same number, then I don't get an answer. Well, it turns out for our problem, I can actually do this. Page 373. There's a table. I've gone all the way up to 1,000 rectangles. What do you think is going to happen if I go to 10,000 or 100,000? These should get closer and closer still. And it turns out that in this case, that limit does exist. And the area in this piece of a parabola turns out to be exactly 1/3. The problem is writing this limit. I got to write it out first. I have to know what limit I've got before I can start evaluating, yes? So let's think about how would we even write this limit? If I can figure out how to write ln, or I can figure out how to write rn in some way, then I can figure out a way to write this sum of all of the areas, and then I can take its limit. How would I even write this? Well, it turns out that I can think of each of my little pieces, the strip across the x-axis. In my example, I was going from 0 to 1. But in general, I'd be going from A to B. And I'm going to divide this up into a whole crap ton of pieces. Here we go. Whole bunch of pieces. To make my life easy for the moment, I will say that all of these pieces are the same width. And since we were talking about an interval from A to B, I'll call these subintervals. I'm going to start counting them. I'm going to start all the way on the left. And I'm going to call this x value A. I'm going to call this x0. The one next to it is x1. The one next to that is x2 and x3 and so on. Until I get to the very end at B. Yeah, if I want n rectangles, then this one should be xn. And that means the one before it should be xn minus 1. And the one before it should be xn minus 2. So if this is xi, this is xi minus 1. And that makes this strip I. So the first strip has as its right end x1. The second strip has as its end x2. The third has its right end be xi. So strip I has xi on its right and xi minus 1 on its left. But I took the strip from B to A and I divided it into n pieces. How wide is any one of those pieces? I take the length of that thing and chop it up into n spots. B minus A is the length. Divide it into n pieces. Let me think about this for a second, because this sounds really familiar to me in terms of tangent lines. I'm thinking of a really small distance along the x direction, right? That's my change in x. I'm even going to call it that. Okay. If I want to do a left sum, then I need to take the left edge and plug it into the equation f of x, right? So my first rectangle would have a height, strip 1 has a height f of x0. This is, by the way, for a left setup. What's strip 2? The height of strip 2. Because I'm going to use this strip and its left edge is x1. And strip 3 is f of x2. And so on. As a matter of fact, strip I will use f of xi minus 1. Yes? I'm just trying to keep my index straight. What's the area of the rectangle in strip 1? Height times width. Same thing for strip 2. Strip 3, all the way to the end, yes? At the very end, the last strip is f of x n minus 1. And now what I've got is the areas, height times width, height times width, height times width. There's a common factor of delta x everywhere there, right? So I could factor that out. And I could say what I really want to do is take f of x0 plus f of x1 plus all the way up to f of xn minus 1, and then I'll multiply by the delta x. Say again? Right, only when the width is the same, but I set it up with the width being the same. Tell me what changes if instead of using the left edge, I use the right edge. The picture will probably be helpful again. People are thinking, let them. Good. What changes if I do a right sum instead of a left sum? What would I subtract? Instead of using this point, xn, I'd use this point. Well, that's the left. So now I need to use this one instead, right? I want the right one. So this isn't going to be n minus 1 anymore. What's it going to be? It's going to be xn. This one isn't going to be x0. x0 is on the left. So instead of using x0 here, what am I going to use? x1. Instead of using x1 here, what am I going to use? I'm going to use x2. So if I go back to this list here, and I say to myself, I want to do the right sum, everything steps to the right one step. I actually don't have to subtract, Hallie. I have to add to my subindex. Which means down here, Rn looks like very, very similar, doesn't it? Now, the hard part in this whole process is figuring out how to turn these choices into something having to do with n, so that I can take the limit as n goes off to infinity, right? Because that's my goal, is to add all this crap up. Now, Riemann liked this idea, but he actually said, you know, I don't always need to use the left. I don't always need to use the right. I could use the point in the middle. I could use a point a third of the way over. I could use different points in different intervals. So he made a generalization, and he said, I'm going to pick xi star in the ith subinterval. So remember, we had a, b, we had xi minus 1 here. I can write I minus 1, and we had xi here. Somewhere in between those, I'm going to pick an x value, and I'm going to call that xi star. And that's the one I'm going to use for my height. It doesn't have to be the left. It doesn't have to be the right. It doesn't even have to be the same every time. It just has to be somewhere in each interval. And then the height is f of xi star. 99.999 times out of 100, we'll either use the left or the right. Every now and then we'll use the middle, but most of the time we'll use the left or the right. Rarely will we ever just say, I don't know, pick whichever one you want. We'll save that for a different class. Intro to theoretical calculus. Not this one. So instead of saying f of x0 or f of x1 like I did up here, I'm going to replace those with my stars. Again, I can factor out the delta x. Now, a new symbol for you. The Greek letter S, sigma, for sum. I'm summing up a bunch of stuff here, right? These are all being summed up. So I'm going to write a capital Greek sigma. And that means sum. What am I summing? I'm summing up all of these heights times widths. Who's taken a programming class ever? Knows anything about coding computers? What I've got is a loop. I want to do this height times width for number 1, height times width for number 2, for 3, for 4, all the way up to n, right? And I want to add all that crap up. So I need to tell you, I want you to start your loop at 1 and end your loop at n. That symbol is referred to as sigma notation for the capital Greek letter sigma, but it's just a shorthand way of writing the loop, add it all up. Riemann said, I'm going to do this, and then I'm going to take the limit as we go to infinity. Now, the problem is, figuring out how to write these points, xi star, whether we want to do a left sum or a right sum or a middle or something different. Once I figure out how to write the sum, I'll be able to figure out how to do this limit. Questions? This looks insane, I know. It just means I picked a spot between xi -1 and xi. The star is my representative choice of point. No, because that's how I figure out what xi and delta x are. I need them, right? Take a look at page 377. On page 377, I see a picture very much like the one I opened class with. I'm going from A to B, but you'll notice that these heights are chosen differently within each strip. In this first strip, it's most of the way to the left. In this third strip, it's closer to the right. In this strip, it looks like it's mostly in the middle. There's no requirement that I pick the same spot within each piece. And that's what the star means. This is x1 star. This is x2 star. I picked a different spot, but the x1 star is in the first strip. x2 star is in the second strip. xi star is in the ith strip. I don't know how many there are. Maybe there are 1,000. This is strip 397. And xn star is in the last one. I could say I always want you to pick the highest point, because then I'd get an overestimate. Yes? I could tell you I want you to always pick the lowest point, because then you'd get an underestimate. But I don't know, is that the left or the right? Depends on whether the function is going up or going down. If it's wiggling back and forth, it could be either. So I want to give myself the freedom of choosing wherever I want. That's what my star means. It can be shown with a lot of work, with epsilons and deltas, that it doesn't matter. If you choose the left side, the right side, or any point in the middle, it doesn't matter. If any of these limits exist, they all exist. So I deliberately picked a weird function, e to the minus x. What's the graph of e to the minus x look like? It's e to the negative x. So instead of going this way, getting bigger on the right, it's going this way and it's getting smaller on the right. So if I actually were to draw this picture, I would see a graph that looked like this. And I only care about what's going on between 0 and 2. So I'm interested in this area right here. I want to try and write a Riemann sum for this area. I want to do it in n. I don't want to pick a number of intervals. Let's do this one with n, and then we can see if we can figure out how to solve it later. But I just want to see if I can write what this sum should look like. If I'm using n subintervals, what's my width? Left side, right side, subtract them to get the width. The width is 2, divided into n pieces. Okay. Let's go back to this idea and the little picture of the strip with all the subintervals listed on it. I'm going to do three versions of this. I'm going to do a left, I'm going to do a right, and then I'll figure out doing a middle. Let's make our choices the left end. Right? There are my little cut up pieces. In strip 1, I want to use this spot, yes? What is the X value there? That's good. Now I want this spot for strip 2. What's that X value? Well, I started at 0, right? And I moved over 1 step. What's the width of my step? I started at 0 and I moved over 1 step. 1 step this wide. What's X3 star? Let's write it the same way. I don't want to simplify it yet. So far, so good? Let's keep going. Eventually, I'm going to get Xi star. Because this will be strip I right here. How many steps have I taken? I've taken I minus 1 steps. So you see how I can figure out how to turn my idea into things having to do with A and B and N. The A and the B are in here, aren't they? They're hiding in this part because that's how we got our width. And now the I and the N tell me how many steps I've got and how many I've taken as I go across. I can now write my Riemann sum. My Riemann sum is f of xi star times delta x. So I get, plug this in to my function. What was my function again? So it'll be e to the negative this thing. Times my width. That's Ln. That's my left area because we use left ends. At this point, I don't know how to do the algebra to figure out what this is, but I've at least written the sum down. Because I have the I minus 1 here, don't I? Because I started with x1 star. I didn't start with an x0 star, did I? But that doesn't matter. It's the first strip. I start counting my strips at strip number 1. That's why I starts at 1. Correct. I is which strip am I in? As a matter of fact, if you go back up here, it says the same thing. Start with strip number 1. Chloe? Because I was just counting as I went through, right? This is strip 1. This is strip 2, and so on. Eventually, I'll get strip N here, right? Somewhere along the middle, I need to call something, right? Let's stop here and say this is the ith strip. Because this loop is in terms of I want to try and write my strips with an I in them. So I say, oh, when I is 1, I'm here. When I is 2, I'm here. When I is 3, dot, dot. Here's I. Because that's what we came up with. I went over 1 step in the second strip. I went over 2 steps in the third strip. So by the time I got to the ith strip, I'd taken 1 fewer step. If I want to be in the 5th strip, 1, 2, 3. I'm in the 5th strip now, but I've only taken 4 steps. I'm very kinesthetic about this. I move my hand, I move my body, the whole thing. It's a feeling. Right. What if I do this for right? How does this change if I do the right end instead of the left end? I promise the change is actually really, really tiny. Say that again. You don't subtract the 1. Because in strip 1, the right end is here. It's 1 step over. And the second strip is 2 steps over. And the third strip is 3 steps over. Chloe, see the difference? Aha! So that means that in this case, xi will be 0 plus I, 2 over n. Not I minus 1. Everything else we did is exactly the same. Rn is e to the negative xi star times delta x. Well, yes, I did. Good catch. Technically, yes, xi star is my choice point. Xi is one of the edges. In this case, my choice point was an edge. So here, no. So let's make one where there is a difference. What if I'm in the middle? There are my strips again. Now I want this spot. What the hell? How far over did I go?
This is a plus 1 divided by 2.
Almost. I take the x value on the left, the x value on the right, and I average them. Yes? The x value on the left is x0. The x value on the right is x1. Notice there are no stars here. But this is our starting point, which we were using 0, and 1 step. Remember, we're going from 0 to 2. So I start here, I move halfway over. What's this x value? That's 1 step. So this point, this midpoint, that's going to be x1 star. X1 star is half of this sum. Yes? It's the average. Which in our case is going to be 0 plus 2 over n over 2, which gives me 1 over n. Half of a step. I didn't go all the way over, I only went to the middle. That's halfway. What's the next one? I need to know this x value. That's 4 over n, right? It's 2 steps. So now I'm going to average those. 2 over n plus 4 over n over 2. You add the fractions, you get 6 over n. You divide by 2, you get 3 over n. Which is 1.5 steps, isn't it? The 2 over n is a whole step, and then the 1 over n is a half a step. What's the next one? The next one here is 3 steps, right? That's 6 over n. So the next choice point is halfway between those two. Wait a minute. It's halfway between 4 over n and 6 over n. It must be 5 over n. Aha! Okay, hang on a second. Strip I. This is the one that's going to be all sorts of messed up with terms of where the eyes are. Okay, wait a second. Dot, dot, dot. Each right edge is a step. If I'm in strip I, the right edge is I steps. The left edge is 1 fewer step. I add those together. And then divide by 2. Wait a second. Wait a second. Dividing by 2 is the same as multiplying by a half, yes? So I bring it out and I flip it over, and I'm going to write this like this. I want you to distribute. Multiply the 1/2 in here. Multiply the 1/2 in here what happens to my 2 over n's? They become 1 over n. Which means I get how many of the 1 over n's? I have 2i minus 1 times 1 over n. Halfway between 2 spots. M n. We had L for left, R for right. We'll have M for middle. Now, my goal over the next couple of classes is to figure out how to actually evaluate this sum. To figure out when I do this and then I take the limit as n goes to infinity, what number do I get? Do I get a number? Does the limit exist? Maybe, maybe not. Hopefully it will. I'd like to do the ones where it does work and not piss over. But how do I actually evaluate this? This is, in my opinion, a non-trivial task, especially with an E in there. That makes it a lot harder. So we'll try and start with some of the easier ones. The idea is the same. I want to write my sum, and then I want to figure out how to evaluate it. Why? There's got to be more to this than just geometry. I can't only be doing this to basically sit here and play with shapes. There's got to be another reason. For a very long time, I had a pickup truck with a broken speedometer. When we got it to work, the speedometer worked, but the odometer stopped. So I couldn't tell you how far I'd gone, but I could tell you how fast I was going. If I walk at 2 miles an hour for a quarter of an hour, does this sound familiar, people? How far have I gone? If I drive at 30 miles an hour for an hour, how far have I gone? If I've gone for 30 miles an hour for an hour and a half, I've gone 45 miles, right? I'm going to say that at different points along my drive, I had different speeds. Starting at this point in time and ending at this point in time. I'll be nice. My velocity will be in miles per hour, and my time will be in hours. So if I say to myself, I was doing a particular speed for a particular length of time, How could I approximate how far I'd gone during this period of time? I could look at my speedometer and I could say I did a certain number of miles per hour for a certain number of hours. What's miles per hour times hours? This area represents a distance. So what happens if I do this a lot? I can figure out how far I've gone, haven't I? Knowing my velocity allows me to figure out my distance. No, but you did. On your homework, where you figured out how far the ball had gone just by knowing its velocity. But did you do a Riemann sum in your homework? This means something. What did you do in the homework? An antiderivative. There must be a connection between doing derivatives and doing these sums. We have stuff to look forward to for next week, but tomorrow's the exam. I will be posting the key to the review sheet and the homework sections in about 2 minutes. If you came in late and you have your homework for me, please give it to me. I will see you all tomorrow.